So now we'll turn to surface of revolution, and you'll see the connection between this and arc length. The When we talk about the surface of revolution, we know we've talked about revolutions before. We've taken a curve, we've revolved it around an axis, and what we were interested in was the volume enclosed by revolving the curve around the axis. Here, what we're interested in is not the volume, but rather the surface area. So we're not asking how much water can fit inside the figure that we form. We're asking how much wallpaper it would take to cover that figure. It's a different question. It's the same sort of operation of forming a solid, but instead of asking, how much volume can fit inside the solid, we're asking how much area is on the outside of the solid. So, in order to understand this, the key is to understand a particular shape, which is called a frustum. And when I think of a frustum, basically this is a frustum right here. And if you've ever watched the Olympics, when they win, when the athletes win, they, depending on whether they come in first, second, or third, they stand on a different height pedestal, and those pedestals look sort of like a frustum. So that's what you should be thinking here. It's this kind of sort of semi-triangular thing, circle that the people stand on. Basically, it's like if you took a cone like this and you simply chopped off the top and ended up with just the bottom there, that's the frustum. So, and you can, as I explain this, of course, if you want to, you can think of me as the gold medalist in calculus, but I won't require that. So anyway, the thing to understand is that the surface area of a frustum, by which I mean, by the way, only the side area, I'm not talking about the top or bottom, I'm just talking about the side area, is given by this formula. It's 2 pi times the big radius, which is here. Since this is a circle on the bottom, that's going to be the big radius, and on the top we have a small radius. So it's going to be the average of the big and small radii times 2 pi, and then times a number called L, which is the slant height. That's the name of that. It's the length of this line. So it's a little easier to see the connection between this and surface area if I draw it with the frustum on its side, which is what I've done right here. What you can see is that now I have the big radius, the small radius, and the slant height written that way. And this is how I would form this, by basically taking this line here and revolving it around the x-axis. That's how I would form that figure. Now, what this has to do with arc length is that basically when we find the surface area, we're adding up the surface area of a whole bunch of frustums. Or maybe frusta is the plural. This is one instance where I can't say I know for certain. So imagine that we have this. We have this curve. This blue object that I've drawn is really a very tiny frustum. What I have is I have a, let me put it in here. What I have is I have a point on the x-axis, and I'm moving a distance dx to the right from that point. We know how to find the arc length from that, the approximate arc length from that point, because we just did that through this formula. That gives us the length of that gives us the length of the hypotenuse that approximates the true arc length. We can think of the surface of revolution as being formed by basically forming a whole bunch of these frustums, and with the hypotenuse that I'm pointing at being the slant height of I know it's a height on its side, but it's the slant height of the frustum. We then have just the 2 radii. But here's the thing to note about the 2 radii. Because dx is such a tiny, tiny, tiny quantity, the difference between this distance and this one is not going to matter. We're just going to treat it as being non-existent, and we're going to say that the 2 slant heights are actually the same. Sorry, not the 2 slant height, the 2 radii are actually the same. That means that the average of the 2 radii is simply the 1 radius. And we know that basically the distance between the curve and the x-axis is just f of x. So what that means is that translating this, actually I'll just write it here, the frustum area is equal to 2 pi r plus r over 2 times L. Well, what do we know? We know that L, for this frustum here, L is equal to the square root of 1 plus f prime of x squared dx, right? And, sorry, I should have put a dx after here. That's the slant height. And we also know that the average of the small and big radii average of small and big radii is just f of x. Why? Because they're essentially the same number. So we're just averaging two instances of the same number. So here it's like I have f of x plus f of x over 2. So in other words, this thing just becomes f of x. So I have L and I have the average of the two radii, and that means that each small frustum has a surface area of 2 pi f of x square root of 1 plus f prime of x squared dx. That's the surface area of each small frustum. So once again, we go to our go-to move for calculus. We add up all the surface areas of all the small frustums, and that gives us a surface area. We write this with a capital S usually. Is the surface area is going to be 2 pi times the integral from a to b of f of x square root of 1 plus f prime of x squared dx. That's if we do it, of course, in the y direction. So this is revolve about x-axis. And if we want to revolve about the y-axis, we would do this in the y direction. And that would come out to g of y square root of 1 plus g prime of y squared dy. This is revolve about the y-axis. And of course, if there's one that you really want to know, this is the one that I think most people remember. This is sort of how I usually think of it. In fact, in previous years, I haven't even solved ones that involve revolving about the y-axis. It's just that our new textbook has a few of those problems. So just know that this is sort of the mirror image situation in the y direction. So there we go. These are the formulas for surface of revolution. One more thing to note, by the way. I just want to go back to a previous drawing. What I've drawn here by these circles is I'm trying to suggest what a surface of revolution would look like. We're talking only about the sides of the object. Technically, there's sort of like an end of, it's almost like the end of a can. You think of a can, it's got a piece of paper wrapped around the can, and then there are the two lids. We're talking about the surface area of the piece of paper, not the two lids on the end. That doesn't count. That's not figured into the surface area of this object that we're calculating. Why? Because the formula is derived from the formula of a frustum, which gives us the formula of this yellow side of the frustum, not the formula for the ends. So there we go. I'll just put up the formulas again. There's the formulas for surface of revolution.